Hi ladies and gentlemen, just want to provide a quick video here that talks a little bit about related rates. This is a really important idea and is oftentimes a source of confusement for students in Calc 1. So I just want to provide you with a little bit of commentary and a single example to help you understand the idea. Obviously it takes practice, but I want you to grasp the concept behind related rates. So what I want to do, first of all, is just briefly talk about the quintessential example. You'll read about this and just to give you an idea of what we're talking about. So a very common example, we have some building here and we have a ladder that's up against the building, something like this. And the related rates problem goes kind of like this. If I grab the bottom of the ladder and I start walking, and let me change colors here, and I just start walking this way with some velocity, then as I'm walking, the top of the ladder is going to slide down the side of the building. And the rates are related. That's where the term related rates comes from. So the rate at which I am pulling on the bottom of the ladder is related to how quickly it's sliding down. The other thing I want you to realize is, obviously, when the ladder is starting its steep up against the edge of the building, as I'm pushing out this way, I have a pretty slow rate of change on the top. As we get to the point where the ladder's almost flat, the last little bit here, the ladder's actually moving very quickly. So this whole idea of, even though I'm moving at a constant rate, the end of the ladder is changing with respect to its rate or its velocity. That's a key component of the idea with related rates. Let me give you a far more important example to help get the idea across. So here we have a horizontal tank. You can think about this as any kind of liquid bearing tank. We see these in tanker trucks, we see these in rail cars, we see these people with landscaping, or sometimes you'll see trucks that have pesticides in them. There are several different types of problems that are related to this type of a tank. And what we're interested in doing is we're interested in understanding the volume and the rate of change of height as we change the volume. So for starters, let me write down the relatively intimidating looking equation for volume as a function of the height of the amount of fluid left in the tank. All right, so we have, of course, volume is going to be the length, which is fixed, multiplied times the cross-sectional area, just like we have with any kind of right circular cylinder. The difference is the area is changing as a function of the height. And so what we have over here is this expression, which includes an arc cosine, and this is going to be the expression that gives us the cross-sectional area. How we come up with that was not really what we're talking about in this problem. What we want to understand, however, is what we have here is volume as a function of height. The radius and the length of the container are fixed. So the only thing that's changing here is the height. And what we're interested in is understanding how does the height change with respect to time if the tank is draining. So we have to think about the fact that height is a function of time, and what we have is we have a rate of change of volume with respect to time. Well, to do this calculation, this is going to be the derivative of the volume, which is a function of height, but the height is a function of time with respect to time. This is what we talked about last week. This is the chain rule. This is going to be equal to the rate of change of the volume with respect to changing height multiplied times the rate at which the height changes with respect to time. And so we can see here that we have a relationship between something that's known, we know how fast the tank is draining, versus something we don't know, which is the rate of change of height. And those two things are connected by the rate of change of volume with respect to changing height. Let's take a look at how this is going to shape up. What I'm going to do is, I'm not going to calculate these derivatives. For those of you who are interested, if I have the derivative of arc cosine, so the derivative of arc cosine of x with respect to x is equal to -1 divided by the square root of 1 minus x squared. So we would need to use that, and we are going to use it when we take this derivative. But let me just, again, I don't want to go through the derivative. You can calculate that on your own. I just want to talk with you about the idea of related rates. So let me just write the derivative down. All right, so this is the expression for the rate of change. Again, we're applying the chain rule here. And what we end up with is L is a constant, so that's just out in front. And then we end up doing the derivative of this expression here, which is going to be the derivatives with respect to h, and then multiplied times the rate of change of h with respect to t. We get this rather innocuous looking expression here. It's not too bad. It does require a fair amount of algebra for us to simplify it to this level. What I want to do now is just look at a specific problem to give you an idea of how we would use this information. Let me write down some of the constants that I want to use. Let's say, for example, our tank has a radius of 3 feet and a length of 15 feet. And what we're going to do then is we're going to take a look at this rate of change of volume. The other thing that we know is the volume is changing with respect to time at the rate of 1 gallon per second. And the conversion there is 13368 cubic feet per second. So there's approximately 8.3 gallons per cubic foot. So, there's about 7.5 gallons per cubic foot. So what I'm going to do is substitute these numbers in, and then we'll have an expression with numbers in. Give me just 1 second. So what I did, you can see here, is I just took and solved our expression here. Rate of change of V is equal to this here. I solved for our item of interest, which is the rate of change of height with respect to time. I also substitute in the numbers that we put in, and I end up with this expression right here for the rate of change of height with respect to time. This is a function of height, which makes sense to us. We have this semicircular shape, and so initially, as the tank is draining, the height is going to be decreasing relatively slowly. And then as the sides come in for a fixed amount of volume, which is leaving 1 gallon per second, then the height is going to be increasing in its rate of decay more quickly as we come in. Okay, so it makes sense, the situation we have here. And what I want to do is just show you a graphic of what this looks like. Here is the function of interest. So when the height is 3 feet, and that's when our tank is halfway full, and you'll see basically these tanks are never filled beyond the halfway point. And so when it's full, when the tank is half filled, which is a full tank, when we're talking about these horizontal cylinders, then the rate of change of height is around 15 thousandths of a foot per second. So that's the rate at which the height is dropping. We have a big tank, right? We have something that's 6 feet across and 15 feet long, and we're only taking a gallon a second out. But then we can see as the height is dropping, so the height is decreasing this way, the rate at which the height is decreasing continues to increase. And then as we get down to the remaining half a foot, which is about the last 6 inches of our tank, then the rate of change of the tank, the height of the fluid in the tank, goes up very quickly in here. And I stopped this graphic at the last inch, 1/12 of 1 foot. And at that point, we have a rate of change of over 6 thousandths of a foot per second. So who would care, right? Why would this make any difference? So, for example, anytime that we would be going along an aircraft, for example, with a tank similar to this that would be shooting pesticides out on top of crops or something like that, right? What's changing is the center of gravity. So the center of gravity is changing as a function of time because the center of gravity is directly related to the height of the fluid that's left in there. So these are the types of things, and as that center of gravity changes, then the aerodynamics of the aircraft, the way in which it handles, those are changing. And so these are the types of examples of when related rates are relevant to us. They show up all the time. I wanted to show you a reasonable example as opposed to the very simple ladder pulling problem which everybody sees. This is a more realistic problem, just to give you an idea of why we're talking about this. Anyway, good luck with your week 5 studies.